I will share the screen and I will try to convey certain messages to you all on this very simple class of equations that although it looks rather simple, but it could be really interesting and just the tip of the icebergs of a huge field that is really active these days. There are great experts all over the world working on homogenizations of elliptic equations. What I'm about to describe to you is just a tiny part of it, and it's very simple. Nevertheless, to me and to some of the people I know, it's rather intriguing, and there are many things that we haven't understood well yet. So my message is that the equations are simple, the models are simple, but we want to go further than just well-postness theory, and we would like to understand really deep about like finer properties of solutions. And this is typically my style. I would try to start with some given pre-lecture notes that I have written down, and then I will start with that pre-written notes on the left, and then I will write more on the right. And some of you actually haven't got the file, so let me try to include it here before I start the pre-lecture notes, and then I will send you Professor Wen judging the post-lecture notes, and then he can distribute to you all. Okay, so I guess yeah. So I just sent the pre-lecture notes. So that's set. Okay, so let me start now. As you can see, this is the first part of the two lectures, and today I will try to do it for 2 hours. Probably we can stop a little bit in the middle so that everyone can relax a bit. So the equation of interest, you can see that I have written on the left here. So this is a Dirichlet problem. I'm highlighting it now. It's the Dirichlet problems of non-divergent form. That I have, it just equals to f on the right, and then I am prescribing the Dirichlet boundary conditions, right? So the typical situation is always that I have a Dirichlet problems on this domain U, and I'm prescribing that U epsilon is equals to G on the boundary, and it's a non-homogeneous problem. I have f on the right. And then inside here, I have an operator, typically of the form f of U epsilon equals to f in U, right? So that's a typical problem. And homogenization theory arises from various different purposes or practical situations. So let me describe maybe 2 or 3 of them, and then I will go into the model and the problems. So how does it arise? So it can arise from essentially a multi-scale problem. So, a multi-scale problems that the problem can have scales in it, right? For example, you can consider like composite materials, in which, the problem has very small fine scales in it, right? It created by different kinds of materials that combining the molecules and the components. So it has a scale, right? And the scales of the problem is some small scale epsilon depending on the problem. So in the practical situations, an epsilon greater than 0 small is a given fixed scale. I mean, for mathematician, epsilon is epsilon. I don't know what is it, but for real applications, they do know what the size of the epsilon. And that's the first example that you can see. the other example that you can see is actually we don't even consider the problem with small scale. You can consider the problem with normal scale, right? So a normal scale problem. So what I mean by normal scale problem is a problem of scale 1. Like we look at, the houses or the roads or the building. Those are, let's say, of our scale, so scale 01. But when you hop on the airplane, you fly up, then you look down, right? Then the problem suddenly, like all the structures becoming small. So what it means is that you are consider the problem of one scale, but then when you zoom out, right, and then you zoom out, then you would see like essentially again a homogenization problem, so a small scale problem again. So that's the other scenario. Or you can also think about it as sort of like the problem with pixels on your screens, right? Each of the pixel can be considered as sort of a one scale, but when you zoom out, you look at the whole screen, then you see sort of like some sort of effective behavior, and that's sort of also a multi-scale problem. And the third example that typically comes from also, it's kind of the same, but this is more mathematical, is also coming from probability. So you can consider sort of like a ZN grid, right? It's just a normal ZN grid, and you can in this kind of problem, you can do a random walk on a ZN grid. So you just start at a point, you do symmetric random walk, left, right, or up, down, with cost going left and right equal, and up and down are equal. So it's symmetric random walk. And then if you again, it's an exact problem on ZN grid, but when you zoom out, you would see, those random walk, discrete and zigzag random walk. When you zoom out, it essentially becoming continuous. And if we consider the value functions, it becomes a solution to this non-divergent form equation. So those are certain motivations and applications that we have in mind. Okay. So for our purposes, we consider the simplest setting. So I would say this is sort of simplest case. Is a prototypical case. This is non-divergent form, elliptic problem. And again, we have a lot of top experts in homogenizations here, like Professor Wen Jiajing or Professor Hiroyo Shimitaka, and others. I couldn't see all the names, so forgive me if I'm missing names. So I mean, the equation of non-divergent form that I'm considering is the equation of just this elliptic type problem, right? Minus aij x of epsilon u epsilon xi xj of x equals to f of x in u, right? And I'm just rewriting the equation, equals to g of x on the boundary. So it's non-divergent form. Non-divergent, right? And I put the assumption of the diffusion matrix on the left. But what I want to emphasize here is that non-divergent form and divergent form are very different. Of course, for elliptic theory, you have seen from Dijorgi, Nash-Moser to Krylov-Safonov, those are very different. But here, even when I assume that the coefficients are extremely smooth, they are different. And I want to tell you why they are different here. So this is really different from the other problems of, normally the divergent form homogenization problem is this. Xj equals to f, maybe f tilde and u epsilon tilde equals to g tilde. Okay, so this is a divergent form problem. By the way, I forgot to say one thing. I'm using Einstein summation conventions here. By that, I mean like repeated indexes mean summations, right? This is twice, or even number of times means summations in that index. Okay, so I'm summing here in I and J. So I want to just tell you very briefly why they are different. And it turns out that the tools and the methods being used in the two different areas in non-divergent and divergent form are very different, are widely different. The reason is very simple, right? You know, let's look at the divergent form equations. Let's just differentiate it, assuming everything is nice, right? So you know, let's say I'm trying to write the divergent form equations in terms of the non-divergent form equations. I'm just expand things out, right? And you see that if I differentiate in the u epsilon xi, then I have exactly this one. Okay, so this is not surprising, right? But however, when I hit the derivative on the diffusion matrix, then because of the parameter epsilon, it's different, right? So this equals to, when I differentiate in that, I would have minus 1 over epsilon aij differentiate in xj of x over epsilon u epsilon to the of xi. And what makes it different is that this parameter 1 over epsilon. If I don't have that sort of small scale, then when I do differentiation, I don't have that that parameter popping out. But here later on, I'm gonna explain, when I let epsilon goes to 0, this one becomes a very large drift term, and it makes the problem very complicated. Actually, there's still a lot of active research going on now when we have a large drift term. So you see that it's already clear that the two problems are different. And on one hand, I would like to say right away that a divergent form equation has energy structure, so you can use integration by parts and do the analysis. So that's the basic and the core methods for divergent form structure. And also you can use energy functional and stuff like that. For non-divergent form structure, it inherits the maximum principle. So the methods are typically, not always, but typically are from maximum principle methods, and you can see it later on. Okay, so that's sort of the description. Okay, so now let me go back to the left panel. I'm gonna mention briefly about the assumptions we are putting and the question of homogenizations. And throughout my lectures, I will try to list like question 1, question 2, and question 3, and so on. So I will try to give you a list of basic and fundamental questions that people have been curious about in this field. Again, this is just the tip of the iceberg and just one equation. It's not all, and it's already very complicated. Okay, so the set of diffusion matrices I am for any I am assuming that I is symmetric, positive, definite. Okay, so and Zn periodic. You know, Zn periodic meaning that you know, I'm just assuming that if you shift by 1 unit, so you start with the y, which is the unit cubed, and you contain all the structures of the diffusions. If you shift it, you know, any integer unit, you see the same structure. And this is an oversimplified assumptions, right? You know, composite material and stuff like that, they have defects and they are not totally periodic, but this is just to make the analysis easy. I can say that the problems of this type for quasi-periodic or almost periodic type, I don't think that there are results on optimal rates. So, and also there's some algebraic rates for more complicated cases, but I'm focusing on the simplest one. Yeah, so we are thinking of a perfect composite material. Everything is beautiful. So the fundamental question that mathematicians and actually people also in practice are asking is that the scale epsilon is small, right? If it's like 10 to the minus 10, and if you want to compute it, you know, by using computers, right, to see the small scale, you would need to have schemes, numerical schemes of scale at least O of epsilon or smaller, right? So it has to be at least 10 to the minus 11, let's say, and that's extremely expensive, and most of the time not reasonable. So both practically and mathematically, we would like to do something, some computations of the macroscopic scale of the O1 scale that is not costly. And it leads to the following sort of theoretical questions, is that what happens if we let epsilon goes to 0, right? Again, epsilon in practice is a fixed scale, but for us, we can imagine, right? So what happens if we keep sort of zooming out, right? We are on the airplane and we keep going higher and higher and higher. If you look down, then maybe everything is becoming sort of like very, like, I don't know. It's hard to say, but like you can see satellite pictures, right? You see lights and dark regions. So those are kind of average sort of behavior, and so it's sort of like letting epsilon goes to 0. So that's a mathematical questions, and it's actually very interesting, right? So we let epsilon goes to 0. We want to see averaging behavior, right? That's sort of the goal. Like, and most of the physics law that I know are macroscopic laws, right? If you punch on the world has sort of really oscillatory sort of behavior if you zoom in, but when you punch it, you have certain laws, and those are mostly macroscopic or averaging law. And so that's sort of the major question of homogenizations. And as a typical example that I often give is that, we actually have seen this thing, right? In when we study real analysis, when we study LP spaces, then we know that if we consider the very highly oscillatory functions like sine of x over epsilon, then it's weakly converges in LP to 0, right? So that's sort of averaging behavior. However, for homogenizations, it's harder, right? Because you're going to see it. Okay. So now let me sort of talk about the ansatz, and then you see I'm using the pre-written notes here, and I'm gonna add more of the details or something I want to convey. I should say that historically homogenizations may be started from Luc-Tatar, and then the famous book by Lyon's Papanicolaou Vardan, and some papers of Papanicolaou and Vardan in this aspect. And the typical method is that we first need to identify the scales. And in this problem, it's simpler. There are only 2 scales, right? And there are some other problems that there are more scales. So only x and x over epsilon. So I'm thinking of x as a so-called macro scale, and y equals to x over epsilon as a micro scale. Why did we say that? Very roughly, right? X is what we see in the O1 level, right? X is X, right? We are in the whole domain U, and X is the scale that we see in the domain U. Okay, and Y equals to X over epsilon. Why did I call it a micro scale? Because if you look at when Y is O1, Y is O1 meaning that X is O epsilon, right? So what YC is sort of like this O epsilon, right? In X equal to O epsilon. So it sees the F scale in the epsilon level. So it sees the macro scale. That's why people call it macro and micro scale. And again, there can be meso scales or some scales in the between. I'm always considering the simplest one. Okay, and what I'm writing down next is the so-called ansatz in applied math, or in the typical study of homogenizations, or this started even from the Newton times, passing down to fluid mechanics course in England earlier, and also still now in Canada, is that people study the problems, they identify the scales, extremely efficiently, and then with the scales they plug in and try to expand things out and try to do formal computations to read up useful informations. So what I'm doing is by no means, new. It's just, essentially trying to capture the asymptotic expansions, right? So ansatz is a guess or guessed formulations or stuff like that. So what we are trying to look at is that we know u epsilon x sort of depends on two scales, right? A variable x and y equals to x over epsilon, right? Again, there can be hidden scales actually, right? Who knows? We don't know, but by guessing, we are just assuming that we see two scales, and then we are trying to do some formal asymptotic expansions to figure things out, right? So the natural way would be that I would try to, expand it out in terms of epsilon power, right? So expands out in epsilon powers. And you can see that, it just naturally to write like u epsilon equals to u0 plus epsilon u1 plus epsilon square u2 plus so on and so forth. That's just a natural way, right? And you can see that, again, I'm not sure if u0, u1, u2 are only depending on two scales, but, I have the luxury to guess, right? It's experimental sort of mental experiments from mathematicians, so we just guess. And so we guess that u0 depending on two scales, u1 also depending on two scales, and so on and so forth, right? And for the convenience purposes, I'm writing it as u0 xy plus epsilon u1 xy plus epsilon square u2 xy, okay? And keep going. And in fact, formally, we can do this computation for all terms. However, checking that rigorously and having meaningful information out of it is not easy. And I'm sorry if I make you feel bored. Some of you, have done this kind of computations for thousands of times, I guess. You're experts in the field. But anyway, so let's just do the computations, right? Maybe let me just say it once and for all. You have UK is the in epsilon to the k, right? So UK we write as UK of x over epsilon, or we write as UK of x and y. So we just need to do the computation once and you see it for all, right? So I need to compute the Hessians of UK in x, right? So this square of UK in x. We just do it by chain rule and normally, right? So if I differentiate in the first lot, then I just have d square of x. Yeah, I'm gonna write as UK of x and y, and I'm gonna use chain rule. So if I differentiate in x here, I will have d square in x of UK of x, y, okay? If I differentiate in y twice, I have 1 over epsilon square popping out, right? So d square in y of UK xy. That's if I differentiating in y. And then, it can be that I differentiate in x once and in y once, right? And it occurs twice. So I have 2 over epsilon d square of xy, or yeah, let's write as dx dy. Dy UK of xy. So that's the computations that I'm using it once and for all in this kind of estimates and business, right? So you see that, although that I wrote a very lengthy box, or lengthy set of computations here, but it's the same. It's for everything, okay? And then again, the tour is just that using this ansatz, and then we do formal computations, and then we plug into the equations, and try to do matching asymptotic, like matching all the epsilon to the k scale. So let's plug in the PDE and sort things out in epsilon to the k. So when I plug in the PDE, I recall this is my PDE, right? So it's I write y is x over epsilon, okay? And if you do that, Yeah, so how should I? Okay, so if you do that, you look at what's the epsilon to the lowest power. It's gonna be, it's actually exactly 1 over epsilon square d square of y here, right? So that's the lowest power term for the expansion. So that terms corresponding to this first operator. So 1 over epsilon square Lyy. You know, Lyy here is just the linear, you know, differential operator that I'm highlighting down here. And then you keep just, you know, collecting the terms. So let's do it. So the next lowest power term is 1 over epsilon. How do I have that? I have it coming here. This is the first term. And then it's coming here. This is the second term, right? Because so I collect 2 of those to have this 1 over epsilon. Lyy u1 plus 2 times Lxy u0. And we keep collecting, right? Maybe let me do it once more. So for the next terms, I have O1 term, right? So O1 terms, I have these terms and this term and one more term, which is U2. I didn't write it down here, but it's epsilon squared times U2. Okay, so that gives me the O1 term. This is that. Okay, and then, you know, it's a normal procedure. It might look complicated, but if you sit down and do it, you know, it just calculus 1, no more than that. Okay, and then matching asymptotics, and we try to dig information out from that. Okay, so far there's no magical. What I put here in the red box in red is actually a so far kind of a sort of probably the most magical thing in homogenizations from the beginning. That was that we assume that there's a separation of scales, you know, or we assuming that x and y are unrelated. Okay, of course this is totally wrong, right? You know, you have y is x over epsilon, so y depends on x. However, you know, if we believe that the scales are separated, right, you know, what changes in the macro scales a little bit doesn't affect what changes in the micro scale, and vice versa, right? If, you know, in my composite material there's a tiny defect, there's something going wrong at just a single locations, maybe I'm hopeful that the whole material is still fine, right? You know, otherwise it would be too bad. You know, I couldn't create something. You know, the shell of the airplane couldn't be all perfect. There should be defects somewhere. But I'm hopeful that what changes in the small scale wouldn't affect the whole macro scales and vice versa. So practically, although it's wrong, right? But practically, uh, the key assumptions, actually, this is I think to me is the most important point to do homogenizations, was that we assume x and y are unrelated. Okay, let's go with that. And you see that once we assume this, without these assumptions, I cannot do anything actually. But once we assume this, then we are good to go. Magic then happen. Okay. Again, you know, I'm sorry if you already know this, but I promise there's something interesting that coming up later. Okay, so separations of scales, x and y, and let me write again here, x and y unrelated. Okay, then you know, if I have the equations for y, right, I'm just now considering x as just an index, right, or a fixed number. Right, so Lyy is minus aij in y of u0 of yi yj xy equals 0, right? So this is a very nice elliptic equations. I have maximum principle or strong maximum principle, right? If it's equal to 0, then it forces that that u0 has to be just constant, right? I mean, that's the only solutions of the equations. And what do I mean by constant?
I
Yes,
have a question.
sure.
So here we are also assuming that U0, I mean, in this formal derivation, we are assuming U0 is periodic in Y. Right? So this equation is posed on the torus.
Yes.
And then the arguments you just showed.
Yes. Yes.
Okay.
Yes. Absolutely. You know, what you say is really important because because if I'm in a you know, like how should I put it? If I'm in RD, right, I can have solutions which are linear, right? I can have just ax a dot y plus b. I can have a linear plan, and clearly that is equal to 0. Oh, hidden here, what I'm assuming already from the beginning is that the problem is being considered for y in the torus, right? So Tn is Rn mod Zn. So because of this, I have that the solution is constant, right? So thanks a lot. And that's why what I'm saying is that when we consider the problems in almost or quasi-periodic or random setting, things are more complicated. Okay, so that's great. So here and also here, constants means what? Constant means that u0 xy is actually independent of y, right? But there's still the x variable, so that means that I have u0 xy equals to u0 of x. Okay, so that's the first deductions, and it's already important, right? Because you see that what it means is that in your asymptotic expansions here, you have u epsilon is kind of like u0, and u0 doesn't see the micro scale anymore. It's only see the macro scales variable, so it's averaging. Okay, again, it's simple, but nevertheless important. Okay, so I guess that I don't have to rewrite the second one because the second one goes in the same way. So I write out the equation for O of 1 over epsilon. I have this operator. And again, you know, once we have got that u0 is independent of y, right? So because u0 is independent of y, I get that when I differentiate in x, I have is 0, right? So so I get the next thing that is u1 is also just depending on x. Okay, so that's the next thing. Put it here, u1 of xy. And also, again, I am thinking of this as a great chance that we can interact. So please stop me and, you know, ask me if you have concerns or other points. So that's great. We are done with the first two, and let's deal with the third one. And the third one is important. O1. So let me highlight it here, and I'm going to rewrite it a little bit. So O1 is that I have Lyy in U2 equals to minus Lxx of U0 minus 2 Lxy of U1 plus f of x. Okay. So from this, I have Lyy in U2 of xy equals to minus Lxx of U0. Let me write down clearly. Minus is, then I have plus Aij in y, U0 of xi xj in x, right? That's minus Lxx of U0. And this one is 0 because U1 doesn't depend on y. So it goes away, plus f of x. Okay? So this is important. And actually, when people do homogenization, they see this equation most of the times. And it turns out that this one is not too easy to be analyzed. Okay, this is O1, and this is not too easy to be analyzed. We need to be careful with this, and you know, for me as well, every time I'm working on this, when I see this one, I need to stare at it for quite a while and try to understand its structure. And after sort of thinking about it, let me recall that x is now fixed, right? It's not moving. It's just a parameter or just a fixed number, vector, I'm sorry. And y is a variable, right? So that's the first observation we can do. The second observation is that I'm lucky here. I'm considering the simplest case. So Lyy is a linear differential operator, right? So those are the two first observations. Okay. So once we realize that x is fixed, and this means that it's a fixed number, you know, u0, xy, xj, x is also a fixed number, right? What varies is you know, the y here and the aijy. So those are what varies. Okay. And since that I have a linear differential operator, I can break things down, right? I have a complicated right-hand side. I can always break it down into simpler blocks and then add things back later on. So, you know, instead of considering the whole right-hand side, which is rather complicated, I'm gonna break it down, right? So break things down to simpler blocks, building blocks, right? And then, you know, later on I can just you know, add things back. This wouldn't work for nonlinear cases, right? But at least you know, it works for linear cases. So if I break things to simpler blocks, then instead of considering the whole thing, now I only need to consider the left-hand side is still that, so it's still a linear operator. But maybe now let me write it in a different way. So I'm just now considering Lyy of something. I'm gonna write maybe V. I'm gonna name it later. Instead of considering the whole thing is complicated, I'm just gonna consider AKL of Y here. So just one term, right? So this is just one part of this thing. And I'm gonna need to add a correction constant. So I call it A bar KL in Tn. So I call this equation KL. Okay, so this is one building block. So this is sort of a basic building block. So once I understand this basic building block, then I would be able to, you know, glue things back together to understand this problem above here, right? So that's sort of the goal. Okay. So that leads me to the problem I put in the black box on the left panel, is that if I fix two parameter k and l from 1 to n, I consider the PDEs that I have Lyy of VKL equals to AKL, and I subtract, you know, this is some correction terms, okay? And AKL is some unknown constants, some correction terms, so that the problem has a solution. That to be described later. Actually, for us, we are in we are considering linear elliptic equations. So the correction terms here, you can think of it as coming out from Fredholm alternatives, nothing more than that. For example, when you learned about linear elliptic equations, when you consider the Neumann problem, and you would need to have some compatibility conditions coming from Fredholm alternative, and this is exactly that. But in general, for general problem in homogenizations, it's always that we're gonna break it into building blocks, and then we always try to solve this problem, and there's this kind of correction term on the right hand side, and later on we're gonna call it effective constants. Okay. Again, we are, you know, I'm because I'm in elliptic equations now, so I'm just gonna call it compatibility constant for now. So here's the theorem. I think that it was surely first done by Papanicolaou and Varadan. So for this theorem 1, I would refer to the results by Papanicolaou, Varadan, And then in the two classical textbooks that I mentioned, right, you know, Lyon's, Papanicolaou, and Vardan, and then and in also in the other textbook, that there exists a unique constant, a bar KL in R, so that the star problem has a solution, VKL. Okay, and again, like what Wenjia asked earlier, it depends if you consider the problem in the whole space, then uniqueness, you know, you need to put boundary condition at infinity, saying that if solution has to be bounded or sublinear. But here I'm in a torus, so I don't have to impose boundary conditions. It's periodic boundary conditions. Okay. Then it has, you know, because this is a elliptic problem, then what is really remarkable is that VKL is unique up to additive constant. So it's unique, solution is unique. You know, of course, if it's a solution, you can add a constant, it's still a solution, but that's all. Okay, so we're going to prove this theorem. Let's accept it for now. Okay, maybe a quick remark is that we're going to call later on that AKL is called the effective constant, right? And the matrix A bar equals to AKL for KL from 1 to n is called effective diffusion matrix. Okay, so that's that. Yep. So let's assume it for now. Please believe me. Anyway, once we believe this, then you know you can see that we have been able to solve the problem for each of the building block, right? You know, so with the problem here, I'm writing down, I'm highlighting in yellow here on the right panel. Once I understand this, I can go back and just add things up, you know, take a linear combinations to have the problem in a complicated way, right? So indeed, I just need to define U2 to be VKLY times U0 in XKXL of X, right? And that leads me to, you know, complete the whole combinations of AIJY, U not XI, XJX. And then that allows me to have, let's just write it down. I have this one, right? Equals to minus AIJ VKL YIYJ U0 XKXLX, okay? And this one is nothing but exactly this one, right? That's let me use a different color. It's exactly these terms that I'm waiting for, right? And minus this one, this is the correction terms, right? So let's compare the two equations. On one hand, I have LYY of U2 equals to AKLY U0 XKXLX plus FX, right? That's on one hand. On the other hand, I have that because of the correction terms, I have is equals to this one. Minus AKL, again, this is the correction terms, right? U0 XKXLX, right? So naturally, those two terms need to match, right? And this is an elliptic equation for U naught, okay, right? So I would have the effective equation for U naught coming out. So U naught as a limit solving this effective equations, okay? So, and that's the result. So I think I'm a bit, I was expecting to, I mean, I expected that I could do this a bit faster, but I'm happy anyway. So in the conclusions, this is typically the case that people would write down in homogenization. I will explain, is that you can see a lot of papers in books in the area. They would say that in conclusions, in the expansions, U epsilon would be like U naught plus epsilon square of U2 XY. I'll explain why. And it looks like this, okay? And again, epsilon square, all of those gonna go away, right? So at the end of the day, U epsilon gonna converge uniformly to U. you see this is uniform conversion, not in L2 or something, because it's using maximum principle, and you're not solving the effective equations, right? Again, AKL is just popping out from nowhere, just some compatibility condition, and suddenly it's solving, helping us to solve the equations. Okay, so that's homogenizations. Okay, so maybe let me write down a heuristic conclusions is that I would have U epsilon behave like U, X behave like UX plus O of epsilon, plus higher order terms. And U0 solves the effective equations, right? Effective equation, minus AKL, U0, XK XL of X equals to F of X. And there is no micro scale here. Right? I don't see X over epsilon or Y variable anymore. I only see the macro scale, and that's the goal homogenization. Okay. All right, so that's great. Maybe let me try to give you the rigorous analysis. I will try to give you a proof of theorem 1, and then we can maybe take a break for 5 minutes. And you know, I think you can ask me questions and stuff like that, and then we do the next hour. Okay, so the rigorous analysis is the understanding of this problem. By the way, I forgot to say this problem is called this. There it has at least 3 names. It has the name like cell problem. Cell problem because it's defined on the cell, right? On the cell y equals to 0, 1 to the n. It's called the corrector problem. I will explain corrector here because it corrects the behavior of d square of U epsilon. I'll explain why is it called corrector problem. And also it has the name ergodic problem. This comes from ergodic control. You know, different names for the same kind of problem. Okay. It just comes from ergodic control, optimal control for first order equations. Okay. Anyway, so let's study this problem. So I have the operators LYY of DKL, which is this one, right? Equals to the right hand side. I have this one, and then remarkably, I have, you know, out from nowhere, I have this sort of correction term. And there are many different ways to study this kind of cell problems. Actually, we can do vanishing discount, and there are, you know, a lot of different ways, especially for nonlinear equations. I'll mention a little bit about nonlinear equations. But since we are in a linear setting, there's an easier way to study this. And in fact, it's written in textbook, right? You can see Evans. You know, the way we are doing here is study this is essentially using Fredholm alternative. I guess this is from Evans chapter 6 or other relevant textbook. Nothing more than that. For the linear equations, and it's famously known that it's always the case. It's useful to look at the adjoint operator, right? That's Fredholm alternative, and I'm not gonna say anything further. So we look at the adjoint operators of L. So, you know, you just, what do I mean by adjoint operator? Here you take L, Y of phi, you test with a test function C, compactly supported. You write to be L star Y of C multiplied with phi. So just that, right? So you just switch the derivatives to the other one. So the adjoint operators for that L star is just nothing but you differentiate like that. So take Ij, Ry, and all together differentiate in Yi and Yj. Okay. So Again, this is just one way to study the cell problem. And it's not so hard to see that 0 is the principal eigenvalue of this operator. Why? Because Ly equal to 0 only has constant solutions, right? Or unique up to additive constant. So the Lyy equals R equal to 0. This has the space of solution is one dimension. So 0 is the principal eigenvalue. Okay. Of course, I mean, one by dimensions here is that it has solutions, positive solutions, and then any S times that is also solutions. Anyway, it's a principal eigenvalue. So I picked this is better. I picked R is this unique solution that is positive, and I normalize its integral to be 1, right? And this is in the literature, this is called the invariant measure. Measures because or actually it's probability measures, right? So it's measure 1. Okay, so it turns out that this R is really important. So R plays the essential role. Here for us. Okay. And by the way, believe it or not, taking the adjoint operator is always a great idea, even for nonlinear cases. You know, that's actually the nonlinear adjoint method. A lot of you here are actually experts on that. So even if the equation is nonlinear, you can linearize it and take the linear adjoint operator, and that gives you the nonlinear adjoint method. Anyway, that's not in our focus. Okay, so once I have this invariant measures in my hands, and handling the problem is easy. And you see, this is exactly Fredholm alternative or compatibility conditions for like Neumann boundary problem in Evans chapter 6, in some homework problem actually, by the end of chapter 6. Okay, so how do I guarantee that these problems has a solutions? It has a solutions if I multiply it with the invariant measures, I have it's equal to 0. So that's compatibility, right? Because you have 0 equals to this integral. There's no boundary conditions here, right? I'm in the torus, right? So so compatibility conditions, compatibility or solvability of the PDE. This one leads to existence and actually also uniqueness of the constant A bar KL right away. I'm sorry, maybe sometimes I write upstairs and downstairs. Yeah, maybe I'm not. Yeah, I'm sorry, I'm not being consistent here. So subscripts and superscripts as the same. Okay. So you know, right? You know, because of the identity we have is that 0 equals to integral in the torus of Lyy VKL multiplied with R, because this one equals to nothing but integral of Lyy stars of R multiplied with VKL, right? This equal to 0. Okay, and this leads me to the fact that I must have the integral on the right hand side here equals 0, and you know, and this leads to exactly solvability of the problem, right? And that's that. So I have been able to determine that AKL is unique, and it's actually determined by this formula right away. Okay, so we are done. Okay, and so I think that let's stop for like 5 minutes. We can chat or have discussions before I move on to you know. So we are done with heuristic derivations. We are done with the existence of effective constants, and then we're gonna do the analysis, and I'll mention to you some of the important questions. Okay, so again, please let me know if you have questions or concerns now. And
Okay, so questions are welcome. So everybody can unmute yourself and ask questions.
By the way, I did send the pre-notes also to here. You guys can see it, right? I mean, in case you
yes.
Okay.
Everybody, if you go to the chatting, yeah, if you click chat, you will see the pre-lecture note that Han sent us.
Yeah, because I have, I have done online teachings for quite a while. So I figured that if I don't write anything and I just keep writing from the beginning, I would be very slow.
Yeah.
And if I do slides, I would be too quick. So I'm doing a compromise of the two.
So any questions? So I have one question is about the, so you always, I think at the beginning you assume A is C2, right?
Yes.
So for example, for this existence and uniqueness of the invariant measure, what are the regularity assumptions that that still gives you this R? And it seems so maybe it can be more general, the results, the homogenization result.
Yes, so actually that's an important question, like in order to, what I'm assuming is that I'm assuming everything is smooth enough so that I can do the analysis later on. You're gonna see why, because I'm gonna differentiate the equations quite a bit. So I start with something rather smooth, and I assume that I have a lot of degree of freedom. However, what is really needed, and yeah, so that's great. Maybe let me make a remark. So remark is that here, let's say that also in the paper by Xiaoqing Wu and Yifeng Yu, is that we assume everything is smooth enough. A is C2 and F and G are CK for K nice enough. Yeah, just to make the analysis easier. So make things easier. To make it actually the most efficient, I believe, is that so later on I was also not trying to optimize it, but with Spragular, we can relax it to A is in 0 alpha in Tn, and if you and I think this is enough. If you try to lower down a bit more of the regularity, then I don't know. And maybe in the next lecture, I will also, I mean, 1 week from today, I will also try to link to some results that when we try to understand W2P estimates, and we use the result by Avellaneda and Lin, and sometimes that we can relax more of the regularity assumptions. What is the optimal ones? I don't know, actually. It's actually a great question. And yeah, I don't know. And also that, yeah, I will mention, for example, now what I'm talking about today, I also don't know. Maybe I should read the literature more, but I also don't know about perforated domain. Rated domains, whatever we are doing here, does it work or not if you keep deleting holes, then yeah, I don't know. Of course there are you wrote papers on that, and so there are a lot of results in divergent form. For non-divergent form, I don't know.
Yeah.
Earlier, when I was younger, then I would not be hesitated to claim something, but now I'm more careful. So I could say that I don't know.
Non-divergence form. Yeah, I think yeah, all the results I know are either its divergence form, and you just generalize the result of Charanescu-Murat. But there actually, for this perforated case, the first paper is actually due to Perpendicular and Varadan. There they use actually they use a probabilistic method. So for non-divergence form, actually probabilistic method is really the